Okay, so we'll be attempting question number 49 from chapter 12.2 of Thomas Calculus, which is chapter on vectors. This question is actually made out of two parts, so I decided to break it down and do the first part first, then the second part. So here's the first part of the question. Although I'm going to explain the question in a bit, if you want to read through the question thoroughly, you should stop the video right here and now. If not, well then, let's carry on. Okay, the question goes like this. A bird flies from its nest in the direction of 5 kilometers north of east at 60 degrees to a tree. Now this is a vector question because the flight of the bird can be considered a vector because it has both a magnitude as well as a direction, as you can see here. So if the bird were to fly along the direction of the vector to the tree, it appears something like this. However, this is not that important as the question is asking for the location of the tree, which obviously we don't know because that's what the question wants us to find out. However, the question does tell us that the nest and the tree are in the xy coordinate plane, and they were kind enough to give us the origin, the point of origin, which is the nest at the point 0, 0. Just to be clear, they want the location of the tree to be in the coordinate system, and that is why we have to solve the problem. Otherwise, the location of the tree would be as simple as 5 kilometers at 60 degrees north of east away from the nest. However, they want it in that xy form, and that's why we have to solve it by resolving the vector into an xy form. Okay, so how do you resolve a vector? First, given any vector on the xy plane, a random vector v for example, with angle theta, to resolve the vector in the x direction, it will be v cosine of theta, and to resolve the vector in the y direction will be once again the vector v sine of theta. Okay, just for understanding, somewhat understanding of how we got v cos theta to resolve the x direction. You know your basic trigonometrical triangle has a hypotenuse, an opposite, and an adjacent. And to get the cos of theta would be the adjacent over the hypotenuse, right? So if we just rename the hypotenuse like a vector v, for example, and that v would be the same as the hypotenuse in that very sense. So the cos of theta would then be the adjacent over vector v. So we take the vector v and we bring it up towards the cos theta, and that's how we get v cos theta, which would equal to the adjacent, or otherwise in the xy form, the x-axis. Alright, now that we know how to resolve the vector, we can get the x position and y position of the tree just by substituting in the values. So for x, if we substitute 5 for v and 60 degrees for theta, actually for both equations, but we're doing this for x now, we substitute that in, we'll finally get an answer of 2.5 if you do it in your calculator, which is also equivalent to 5/2 in fractions. Now we practically do the same thing for y, substitute in the same values because the vector is the same and the angle is the same, except we're using sine. So 5 sine of 60 would give you a value of approximately 4.33, or in fractions 5/3/2. Alright, so now that we've resolved the vector, we can substitute the answers to get the position of the tree. Because this is done in the x and y axis, so we just substitute that in. We get 2.5 in the x direction and 4.33 in the y direction. Another notable thing is how the vector can be written. The vector 5 km at 60 degrees north of east can be written in the form of I and j, which is how most vectors are written, which is 2.5i and 4.33j. I is in the x direction and j is in the y direction. Now, if you want to check if you have resolved the vector properly, the magnitude of the vector should be exactly the same as the original vector before you resolved it. In this case, 5 kilometers, which is 5 in this sense. So what you do is you take the components that you got earlier, the one up there, and you square each of these components. And after you square these components, you add them up and take the square root of that addition. So I'm going to write them in fraction form this time, because it'll be more accurate that way. So 502 squared, adding with 5 root of 3 over 2, and then we square that as well. So after you do that, the final vector should actually be, the final vector magnitude should be 5. Now, another interesting point to learn is to get the unit vector, which is the direction of vector in the magnitude of 1. So it's quite simple. If you already have the vector and the magnitude, it's just the vector over the magnitude. So the vector that we got is 2.5i plus 4.33j, and we just divide it with the magnitude, which is 5. So that's how you get a unit vector. Okay, so for the second half of the question, it's just finding a telephone pole at 10 kilometers southeast of the tree. So just the position again, and using the exact same method, except we're adding on to the original position that we found earlier, which was the tree. So just in case you wanted to know, here's how we do it. To find the location x, the second position, we take the new vector, which is the 10 kilometers, and cast it with the new angle, which is 45 degrees. And what we do is we add it to the original vector, original position that we got. So 10 cos 45 plus with 2.5, which was the original x position that we got for the tree. So what you get is 7.07, and you add it at 2.5, the final position of the telephone pole should be at 9.57. Or, if written in fraction form, it's really long, 502 plus with 10 root 2 over 2. Now for the y position, it's slightly trickier. Because it's heading in the negative j direction, we're gonna minus the vector, because the vector is heading downwards. So we're going to take the initial position of the tree, 4.33, minus the vector given here, which is 7.07, because using the same formula, 10 sine with 45 degrees. And the final position you get is negative 2.7, or if you write in fractions, 5 root 3 over 2 minus 10 root 2 over 2. And yeah, that's how you get the two positions of the telephone pole. Okay, just in case you didn't catch the final answer, it should be at 9.57 and negative 2.74 in respect to the x and y axis. Or in fraction form, 5 over 2 plus 10 root 2 over 2, and for the y, 5 root 3 over 2 minus 10 root 2 over 2. This has been a group Eric and Jocelyn, since we don't have any other name, and thank you for your time. And I hope you understood whatever we just put up here. Thank you.